So in this video, this should be a short one. We're going to go over couple moments. So I believe on the lecture videos, it's called couples, but I think it's easier to understand when it's called couple moments. I can't remember if they called it that. It doesn't really matter. All you need to know is that it's a special type of moment, which is incredibly important because you have to understand that it causes rotation, which I'll explain in a second. But it essentially is a pair of forces that are equal in magnitude and opposite in direction that causes rotation. If you think about it, put your pen on your table, push up on the inky part and down on the clinky part equally hard, it'll rotate. And in fact, it'll pivot at the point halfway between those 2 points. So logically, you're already doing this, or you already understand it logically by observing that the pen is happening or the pen is pivoting. But because it's a moment and because in this class it's only occurring in 2D, you can use the equation for like the two-dimensional moment that we've already been using in the past. And that is that the moment is the force times the perpendicular distance. So there's two different things I wanted to go over. For now, ignore the red part. Look only at the green 100-pound forces. Okay? So looking at this equation and looking at the 100-pound forces, let's jump into it. So for the 100-pound forces, the couple generated by those forces is the magnitude of the force, so 100 pounds. Oh, well, I kind of blew it on this one, but if this is point A, and this is point B, and this is, we'll just say 2 feet. Well, I blew that answer, but the perpendicular distance there is going to be 2 feet. So the couple generated by these two forces that are definitely equal in magnitude and definitely opposite in direction, they're definitely parallel to each other, so they are couples. So the moment generated by those is going to be 200 foot-pounds. Is it going to rotate clockwise or counterclockwise? In this case, it's going to go clockwise. And you don't necessarily have to put a point of application in this situation because it's always going to rotate about the point halfway through, which is not usually given as a point. So this is your final answer for that problem. But let's take a look. I'm going to try to erase the entire 100 example actually. Okay, so let's look just at the 50-pound one. And maybe I'm going to erase this part too. Sorry. But so looking at just the 50 part one, just like everything that we've been doing at an angle, my recommendation would be to adjust it to a vertical and horizontal component. Why? Because now the perpendicular distances are much easier to understand. I'm going to say that this angle is, we'll call it 50, which means this angle is 50. Okay, so now that we have two components, we have to look at two different couples generated because if the overall force is equal in magnitude and opposite in direction, so will its components. So if we're looking at, we'll look at X. Oh, that's definitely Y. We'll look at Y and X. So if we're looking at X, what's the magnitude going to be? So we have the couple equals the magnitude of that force in the X direction. So we know it's going to be some scaled version of 50. Which trig function do we use? Well, since we're looking at the X direction, we look at the part, and I mean, in this case, the X direction is the direction touching that little arc, which means that we use the cosine of the angle labeled. Oh, I didn't realize they were both 50. That's kind of weird. But anyway, we use the cosine of that angle, and then we look at the perpendicular distance between this X component and this X component. because these are pulling at each other in equally, like they're not only parallel, but they're collinear, the perpendicular distance is 0. So in that case, even though they are equal magnitude, opposite in direction, the couple from these two forces, like these two components of this force, is 0, which makes sense because if you lay your pen on the table and pull horizontally at the clicky part and horizontally at the inky part, your pen's not going to rotate. And if you're doing it in equal and opposite directions perfectly, it won't even move. But now let's look at y. So for y, the couple is still going to be the magnitude of the force, which is some scale of 50. And because it is the side opposite to this angle, or the side that it's not touching, it's going to be the sine of that 50 degrees. And it's going to be the same 2 feet because this distance from the side of this all the way over to where the side of the other one would be, if we continued this line of action down, is 2 feet. So I don't know what that number comes out to, but it would essentially be 100 sine 50 foot-pounds. What direction? Well, if this side's going up, this side's going down, this pen is going to pivot that way. So counterclockwise. And again, you don't necessarily need to put an about point whatever. So again, this is exactly something that we've been doing so far. It's just a kind of weird combination of some things because of the different version of this perpendicular and because of the possibility that the components that you're looking at, like they were here, these two components had a perpendicular distance of 0 because their lines of action are exactly overlapping. So there's a couple things you have to check for, but other than those two things, it's exactly the same as the moments equations. So this is a really short video. I just wanted to go over this and clarify the things to look for.